So welcome. Hi ho, secular neighborinos, and happy Friday. What a week. In just 1 week, 1,000 people showed up on a Monday in surprise to protest a concentration camp in their neighborhood. And the next day, on Tuesday, over 160 people signed up to speak, and all but two were opposed to a concentration camp going into their neighborhood. Most of them for the right reasons. Last night, I went to the Phoenix Union High School District board meeting, and so did dozens of other people to demand the resignation of appointed school board member Jeremiah Cota, who went to a white nationalist holiday party. And all over the state and nation, students walked out of classes to protest ICE on their campuses. We even provided a DIY form for any student who is facing consequences for their civic engagement. I'm sure Lindsay's probably dropping it in the chat right now. So please do me a favor because everything's terrible. January was 11 months long. It was horrible. So please put into the chat your positive stories of civic engagement from 2026, all 5 weeks of it, and share anything that might be happening this weekend or next. Tomorrow, a bunch of us godless heathens will participate in the Signs Over the 60 protest, and we have Gilbert Road. So if any of you would like to do some nonviolent resistance on a Saturday afternoon, we will be meeting around 12:30, 12:45 at the Gilbert Road overpass. And our message is going to be pro-science. So what better way to segue to our guest introduction? Because folks, no Rage Friday today. It is a Science Friday. And today we are speaking with Dr. Ethan Siegel to discuss his latest book, The Grand Cosmic Story, an illustrated timeline, 13.8 billion years and beyond. The book is described as the story of everything from the Big Bang to the far-off future, 100 million years at a time, told in illuminating text and imaginative illustrations that portray every phase of our comic history. So I recommend checking out your Changing Hands or other local bookstore to support his work. Dr. Siegel was born in New York, graduated from Northwestern, and obtained his PhD in theoretical astrophysics from the University of Florida in 2006. In 2008, he moved to the Pacific Northwest, becoming a professor at the University of Portland and then Lewis and Clark College, while also beginning a career as a science communicator, writing the popular and prolific blog Starts with a Bang. Since 2015, he's been a full-time science communicator, including writing, podcasting, authoring books, and presenting science to audiences all over the world. His sixth and most recent book, The Grand Cosmic Story, was just published by National Geographic. So, Dr. Siegel or Ethan, whatever you prefer, did I miss anything from your bio?
You did great. The only thing that's maybe relevant to your audience that you didn't talk about is from 2007 to 2008, I lived in Arizona because I was a postdoc at the University of Arizona in Tucson, Arizona. And so I do have an Arizona connection, and I am sympathetic to a lot of the uphill battles you folks are fighting trying to get recognized for science, reality, and truthful facts in the state.
Yeah. I bet that you've probably been to the Tucson Festival of Books then.
I sure have, and I've been to the Gem Show as well, which I believe just concluded.
Yep, it sure did. Yeah, we're looking forward. We always get a booth at the Arizona Festival of Books. It's one of my favorite events, and there's going to be some really, really great authors there this year. So I don't want to take any more of your time. You've got a lot to talk about. I'm going to hand it right over to you. And folks, go ahead and ask questions, but we're going to probably wait till the end to take any questions. So feel free to engage in the chat, and I will monitor it. And with that, Ethan, you can take it away.
All right. Well, I think the first thing I should do is I should probably share my screen and get my slides up there. Hopefully that looks good to everyone. And you can see that you can call me Ethan. I am Dr. Ethan Siegel. I have written a book called The Grand Cosmic Story. It is beautiful. It is published by National Geographic. And the only people who have given negative reviews are people that are mad that the book is what's advertised instead of the book that they wish it was. So if you wish it was a different book, you might be disappointed, but I think what's in there is pretty great. Because what we do in this book, The Grand Cosmic Story, is we start before the Big Bang, back in the early period of cosmic inflation. And every time you turn the page, you come forward 100 million years in cosmic history to the Big Bang, where you have an illustration on one side of the page, and then you have stories on the other side of the page that I have written. So they're pretty good, I think. And they tell you what's going on at that epoch, at that moment in cosmic history. And we also give you stats for what's happening at that time. How many stars are there? How many planets are there? How many inhabited planets are there? Based on what we know about life, how has life evolved in the universe, and what are the uncertainties on how much life there is? So we go through all of that. After 138 steps, we come to the present day, 13.8 billion years after the Big Bang. And then we give three different alternative timelines for what humanity will do in the universe before we arrive at the actual end of everything. So with all of that in mind, that's what the grand cosmic story is, I figured let's all give you a bonus, because I'm sure you're all going to get and read and gift this book to your curious loved ones. But why not give you something that isn't in the book and tell you about what we commonly think of as the grand cosmic story? We usually take a pretty human-centric view of things and say, yes, yes, the universe started with the Big Bang a long, long time ago. And then we formed stars, generation after generation of stars. They live, they die, boom, they return there polluted, processed, heavy element rich matter that they made inside those stars to the greater universe, which leads to new generations of stars and new star forming regions. And one of them happened to form our solar system some 4.5 and change billion years ago. And after some time had passed, that led to planet Earth, which we have gone to space and photographed both from near and from far. And that's it, right? Well, that's great. That's what we know happened here on Earth. But what does this mean for the rest of the universe? What is our grand cosmic history in context of everything else? Now, many of you have probably seen some graphs like this where it shows like, oh yeah, we started with some Big Bang and there was some early phase of cosmic inflation, and then we had cosmic evolution where it cooled, and we had the dark ages, and then we made stars, and then we made galaxies, and then the universe became transparent to visible light, and we have modern galaxies, and we arrive at today. But how do we arrive at this picture? How do we make sense of this? It turns out you can't just look at the universe and immediately know everything that happened. You have to go through a wide range of scientific endeavors to make sense of it. If you want to understand what happened here on planet Earth, you need to understand what happens in the universe biologically, geologically, chemically, atomically, and even at the subatomic level. And if you want to investigate these things on Earth and elsewhere, there's a whole slew of fields you have to study in order to know it. You need to know about planetary science and exoplanet science. You need to know about stellar history, star formation history, and also the history of galaxy formation and galaxy mergers. You need to understand this in the context of cosmology within the expanding universe, and with the concept that where we are today came from some earlier, more beginning state. And that if we understand the laws of physics that govern the universe and how we got here today, we can then figure out how things will continue to evolve into the far future. So we have to take all of this into account if we want to tell the grand cosmic story that unites us all. Now, a lot of us, when we think about evolution, we have a picture like this, because this simplified picture is what we have shown, that like, oh yeah, like our ancestors were apes, were these old world apes, and eventually we evolved into more hominid like creatures that walked more upright, and we switched from using primitive tools like rocks to clubs to making our own tools like spears, and now we walk fully upright, we're very intelligent, blah blah blah. Of course, this is a very simple overly naive picture of the history of life on Earth. A more comprehensive picture probably looks something like this, where you say early on, we're going to start with where we had life originate for the first time. And perhaps there are some branches on that tree of life early on that went extinct, that haven't survived. But some of those lineages did survive and diversify so that there weren't just bacteria, but there were bacteria and archaea. And that eventually we evolved eukaryotic life that didn't just have protoplasm and non-differentiated, gunk within it, that we had organelles, specialized functions that evolved, things like mitochondria that once were their own organism that then got absorbed into eukaryotic life. And this led to far more complicated things. Eventually, we gave rise to the protists, and then we gave rise to fungi, and then plants and animals came after that. And what we think of as the huge diversity of life we see on Earth, it's a relatively recent development. And we know this because we go back in several ways. One of them is through the fossil record. You look back at the fossil record and you find the lower you go, the deeper layer you go, you find different sets of organisms that lived, thrived, and maybe dominated the biomass on Earth at different times. We can see where the different layers are. We can match them up on different continents from one another. And that's how we determined that the way the Earth's continents and oceans are today is not the way they were in the past. That we have this complex series of not just plate tectonics, but of motion of subterranean layers under the Earth. And so, yes, we know some of our history about how these things have evolved, about how the continents went from being mega continents to separate continents and back again. How we had super oceans where one ocean would cover more than an entire hemisphere of Earth, back to, oh, now we have several different oceans like we have today. And part of what's happening is not just what we see on the surface, but also underneath the Earth. That when we have the Earth, we have these different layers, like we have the lithosphere, which is the crust and the uppermost mantle together. That's why you get subduction zones where things fall beneath, and this recycles some of the terrestrial material back into Earth's mantle. You have mantle sliding, where the lithosphere slides over what we call the asthenosphere. You have parts of the mantle that convect, where you get upper mantle convection. You have parts of the mantle that convect, where you get whole mantle convection. And then you have exchange boundaries between the mantle, the outer core, the inner core, and as we've just learned recently, too recent for this diagram even, is there's an innermost core inside the inner core that is still different again. So when we think about our Earth, I don't want you to just think about it as the Earth as it is today, with its clouds, its continents in its present configuration, its oceans, the life on the surface, etc. Earth has been through many periods where it's looked very differently. This plays a huge role because today we look for exoplanets. One of our big goals is to find an Earth-like planet. But for most of its history, Earth didn't look like Earth looks today. For example, there were periods of Earth where it was completely ice-free. This is a view of the North Polar region of Earth if there were no ice there. This is what Earth looks like when we are not in or entering or coming out of an ice age. During a lot of Earth's history, we have no polar ice. On the other hand, we went through periods, including one that was 300 million years long, where Earth was entirely frozen over, where we had this snowball Earth set of conditions. And very early on in Earth's history, possibly even before life arose on it, we had this condition called Hadean Earth, where it's named after Hades, the god of the underworld, because it was so hellish. and lava filled and unrecognizable compared to what it is today. And if you're like, oh, Earth was never like that, no, dude, we sure were, because 4.5 billion years ago, maybe 50 million years after the solar system formed, proto Earth got struck by a very large protoplanet that we now call Theia. And this kicked up a huge cloud of debris, and it created a dusty torus like structure known as a synestia, which gave rise to modern Earth at the center and our moon. Maybe within 100 million years or so after that. And the moon has changed distance to the Earth over time, and the Earth's rotation rate has changed over time. And again, we see evidence for that in the fossil record. So then you say, okay, great, that's Earth's history. Where are the other Earths? How do we know we're not the only one? And the first mission that really showed us what's out there was the Kepler mission. That with NASA's Kepler mission, what it did was it said, I'm going to point at this field of view, this star-rich field of view. I'm looking down one of the spiral arms in the Milky Way, but I'm looking just out of the galactic plane, so I don't have all that dust and polluting matter in the way. So what I'm going to test for is when I watch these individual stars, their constant brightness, constant brightness. Yes, some of them are variable stars. I'm not interested in those. But what about the ones of constant brightness? Every once in a while, they'll appear to get a little bit fainter, and then they'll re-brighten again. And if that happens multiple times, if I build up, oh, it dims by the same amount, a few days, weeks, months, or years later, that's evidence for what we call a planetary transit. So this is how you get an exoplanet candidate. Now, when NASA's Kepler mission came out, I asked one of the scientists who was working on it, I said to her, you think NASA's Kepler is doing a great job because of all of the planetary candidates you identify, about 50% of them turn out to be planets. They turned out to be confirmed exoplanets. The other 50%, they weren't. They turned out to be eclipsing binary stars mostly. And that's what was causing the brightness variation. And I said, why would you think you're doing such a good job at 50%? And she said to me, oh, because before Kepler, our false positive rate was 90%. And now, after Kepler, because of all the lessons we learned, our false positive rate is down below 20%. So we're learning, we're doing better. What you see as like, oh, 50% isn't very good is actually a step towards knowing what we're looking at and getting it right. And that's because before Kepler, we had about 100 known exoplanets. And now in the post-Kepler era, in fact, late last year, we just hit our 6,000th confirmed exoplanet. And remember, back in 1990, we didn't know any. So really here in the last 3-4 decades, we've gone from nothing to over 6,000 confirmed planets. And what's kind of remarkable about this is we can say, well, I don't want to just look at the planets. I want to take something like the Gaia mission and look at all the stars. And I want to map out all the stars in the Milky Way. And I want to compare them with the stars that are known to have planets. And there's a weird little thing that you notice. One of them is that if you look at all the stars that have planets, you can study something called their metallicity. This is one of my favorite astronomical misnomers. If you were like, I don't like how normal people classify metals versus non-metals. Do it like an astronomer. There's hydrogen and helium, and everything else is a metal to an astronomer because the universe made hydrogen and helium in copious amounts during the Big Bang. Afterwards, all that other stuff only gets made in stars. So everything that gets made in stars, we say that's a metal. Lithium, metal. Carbon, metal. Oxygen, breathable metal. Neon, inert metal, right? It's all metals. Sulfur, volcanic metal, right? It doesn't matter. They call it all metals. If you look at a star like the sun and say, what about stars like the sun? based on if they have as many metals as the sun has, how likely are they to have planets? And the answer is at least 80%, maybe up to 100% of stars like our sun have metals. In fact, you can go down to about a quarter of the amount of metals in our sun and get the same thing. But if you drop below 25%, down to about 10% in that range, it gets a lot rarer. It's very hard to find stars with planets around them at lower metallicities. And if you go lower than that, below 10%, there are only like 10 systems that we know of that have planets. And finally, if you go down between like 2 and 4% below that, none of the stars we know of have planets. So that tells you you need to have a certain amount of heavy elements in you when you form to make planets at all. So when we use a satellite like Gaia and look at the Milky Way, we can map out where are these heavy elements located? And you see that you have higher metallicities, higher heavy element contents, and a greater likelihood of having planets when you are close to the galactic center and in the galactic plane. In this map, where you see the red colors and to a lesser extent the yellowish colors, you're very likely to have planets. But if you see the blue colors, you are extremely unlikely to have planets. And so that's kind of where we are. We know you need to have the universe do stuff, have stars, form stars, have the stars live and die, and return that processed material that was in the stars that died back to the universe over and over and over again until you build up enough heavy elements or metals to an astronomer that you can have not just stars, but planets as well. And fortunately, we know of tremendous numbers of ways to have stars live, die, and return their elements to the greater universe. We can have supernova, and we see the heavy elements in the supernova remnants. You can have kilonova, where you have two neutron stars that merge together and go kaboom, and all the heavy elements get splattered across the universe. Or you could have planetary nebulae. You can have sun-like stars that die and blow off their outer layers. You can have two types of supernovae that make elements that get returned to the universe. You can have a massive star that undergoes a core collapse. Boom, that's a type 2 supernova. Great way to get elements back in the universe. You could also have two white dwarfs, corpses of sun-like stars that merge together. Boom, that's a type 1a supernova. So we have all of these different stars that form in all of these different masses anytime you form stars. And the most massive ones, the shortest lived ones, they burn through their fuel the fastest, they shine the brightest, but they live the shortest amount of time. If any of you are fans of the movie Blade Runner, you might remember this famous line that the flame that burns twice as bright only lives half as long. And for stars, it's way worse than that. If you had twice the mass of the sun, you shine like 10 times as bright, but you only live like 1/8 as long. Our sun is going to live for around 10 or 12 billion years. A star twice the mass of the sun is only going to live for like 2 billion years tops. A star that's 5 times as massive as the sun is only going to live for a few 100 million years. And a star that's 20 times as massive as the sun when it's born is only going to live for maybe 10 million years or under. The most massive stars of all, at hundreds of solar masses, they might live just 1 or 2 million years, period, before dying. Meanwhile, stars that are less massive than the sun are going to live for a really long time. Our universe today is only about 13.8 billion years old, marked since the start of the hot Big Bang. We have stars less massive than our sun that are going to live for tens of billions, hundreds of billions, even trillions or tens or hundreds of trillions of years. The lower in mass you go, the slower you burn through your fuel. And so it's possible that long after all the sun-like stars have burned out, there will still be these lower mass stars that still have life on them. Or maybe that life will arise on them long after we're gone. We know this because we look at stars that form today in the nearby universe, and we find all the different stellar types. The more recently you form stars, the brighter and bluer and hotter the most extreme stars we find in there are. But we don't just have to look nearby. What we can do is we can look back all across cosmic time and say, what was the star formation rate throughout cosmic time? And what we learn is that today, the star formation rate we see today is just a trickle of what it was at its peak, because we've mapped it out over cosmic time. If you look farther and farther away, you find that there are more star bursting galaxies, galaxies undergoing extreme episodes of star formation. You find that there are more and more galaxies where the star formation rate is greater, where there's more gas forming more stars, there's more galaxies merging, there's more, right? Dark energy hasn't torn the universe apart like it's already been doing for 6 billion years here. So if you go back, you find that we hit the peak of star formation about 3 billion years after the Big Bang. And that as you come forward from that peak to today, the star formation rate declines and declines and declines. And today, it's only about 3% of what it was at its peak, which means nearly all of the stars that will ever form in the universe have already formed. And in fact, over 75% of the stars that formed in the universe formed during the first half of cosmic history. And the second half of cosmic history, the most recent 7 billion years or so, we formed less than a quarter of all the stars that exist today. But if you go back earlier and earlier and earlier, it's not, yeah, the star formation rate dropped because it built up and up and up over time. But if you go early on, in theory, and we have never seen this yet, not even with the James Webb Space Telescope, the universe should have formed stars for the very first time. There should have been stars made out of that pristine material from the Big Bang. Hydrogen and helium alone. Yeah, there's like 0.0000001% lithium. It doesn't really play a big role. It's hydrogen and helium, 99.999999% plus is hydrogen and helium. It's pretty good. But today, we see the modern universe, right? And this is kind of interesting because here in this shot, you can see some foreground stars within the Milky Way. You see the close nearby big spiral galaxy, NGC 7331. But then in the background, you see what look like smaller galaxies. And what I find interesting about these pictures is when you see those smaller galaxies, you don't know right away whether they are smaller galaxies or whether they're big galaxies that are just farther away, so they appear smaller. So what we can do is we can measure within the context of the expanding universe how shifted is the light from these galaxies. Because when a galaxy emits light, that light travels through the universe before it arrives at your eye. But all this time, as that light travels, the space between distant galaxies is expanding because the universe is expanding. Well, you know how light works. Light is a wave, it's a photon with a wavelength. And as the universe stretches, the wavelength of your light stretches also and gets longer. Longer wavelength light is redder. So when we say, I'm going to look at these different galaxies, these distant galaxies, you measure their redshift, that gives you the idea of how far away are they? How long has its light been traveling through the universe? And if I want to shift that light back into the same wavelengths of light that, governs how all atoms work, I can figure out what things were like when that light was emitted. Even back before the James Webb Space Telescope era, we knew that modern galaxies, like the Milky Way, were intrinsically red, which means that, I told you when you form stars, you get stars of all the different colors. But as time goes on, the bluest, shortest lived ones die. So today, in our modern universe, galaxies are pretty intrinsically red because most of the stars within them formed long ago. All of the hot blue ones have died, but going earlier in time, we see galaxies that are less evolved, that are bluer, that are lower in mass, that have higher star formation rates. We see evidence of an evolving universe, and in particular, a universe that was more pristine early on and that is less pristine and more, if you're negative about it, polluted, if you're positive about it, enriched than it was at early times. So this is continued into the James Webb Space Telescope era, where we find these ultra distant galaxies in what you might recognize as the first James Webb Space Telescope deep field image. And you can see, yeah, these galaxies are blurry, but they're bright, they're compact, they're rapidly star forming. That's what we expected. All the way back to the current record holder, MOMZ14, which is funny because it's named MOM because it was not the mother of all galaxies, but because it was Mirage or Miracle was the name of the study, and it's not miraculous because even in this galaxy, whose light comes to us from when the universe was just 2% of its current age, 280 million years after the Big Bang, this is still not the first generation of stars. This is still an evolved, massive galaxy full of heavy elements, because part of how we determined how far away it is it has emission lines, not just from hydrogen, but from carbon, from nitrogen, from oxygen in varying states of ionization. And it's by identifying those lines that we can be confident of this galaxy really does come to us from that long ago. So you have this picture and you say, okay, universe, Big Bang, expands, cools, and eventually gives rise to the universe we know today, full of stars and galaxies. But what happened in those in between times? How did we get to there? So you can say, all right, well, at some point, we must have had this really hot epic over on the left side, where I'll just call it, the original name for it was so much cooler. We called it the primeval fireball, because that was the hot, dense, ionized plasma state that existed early on after the Big Bang, where you might have positively and negatively charged things and a bunch of high energy photons, but you don't make any bound states of things, because the instant you do, they get blasted apart immediately. Finally, the universe cools, and now you can form protons and neutrons without blasting them apart. That's great. Now you can have your protons and neutrons fuse into heavier atomic nuclei like helium without blasting them apart. That's great. And then things cool enough that you can finally form neutral atoms without having them immediately be blasted apart, a process that takes almost 500,000 years from the start of the Big Bang until you get neutral atoms. But we see the evidence for that. The leftover glow from that epoch is the cosmic microwave background, discovered in 1965, maybe 64 when they saw the signs of it first. That was hailed as the smoking gun for the Big Bang. And still, we can go back earlier to before you had protons and neutrons, you had a quark gluon plasma. Before you had a quark gluon plasma, you had a plasma full of matter and antimatter in equal amounts. And we can extrapolate back and back and back and back all the way until you get to what you imagine was the Big Bang. And this is kind of the classic picture of the Big Bang. 60s, 70s, into the 80s, we thought this is how reality works. Hot, dense, expanding universe, expands, cools, expand, cools, evolved, and then we get our star, galaxy, planet, and even life-rich, hopefully, universe that we have today. But this story is not complete. It was realized back in 1979 by a then young scientist named Alan Guth that this old Big Bang story is incomplete. And there were four big puzzles, right? This is how science advances, by the way. We don't say like, oh, like I had a new idea, let's imagine it's true. We say, no, I need my idea to be motivated by unsolved puzzles in today's universe. So, for example, if the universe started from this singularity and boom, hot Big Bang in all directions, how come when I look over there, 46 billion light years away. And when I look in the opposite direction, 46 billion light years away. Why do those disconnected regions of the universe that haven't had time to talk to each other, exchange information, or thermalize, come to the same temperature? Why do they have the same temperatures? Why, if the universe could have been curved in any way, like a sphere, like a saddle, or like a Pringles chip, or completely flat, why does it choose perfectly flat? Why is our universe perfectly flat spatially? If things got up to these arbitrarily high temperatures, all of our physical theories that allow us to get the mysteries that we don't know how to solve in the universe solved today, they all predict leftover high energy relics. Things like, which leads to things like proton decay, which leads to things like right-handed neutrinos, which leads to things like magnetic monopoles. We don't see any of them. We've searched for them. Where are they? And finally, we don't live in a perfectly uniform universe. We have a universe that's clumpy. It's filled with galaxies and groups of galaxies and clusters of galaxies and a grand cosmic web with great Swiss cheese like holes in it, these big cosmic voids. That had to grow from some seed imperfections. So, where did they come from? So, this is why we say it's incomplete. The big idea that they had in the early 80s was we could solve this if we had an inflating universe. Imagine, instead of expanding, right? Old Big Bang, you think, okay, we started with a Big Bang. The universe is expanding rapidly, starts expanding rapidly, but it's also full of stuff, matter and radiation, for example, that gravitates. So it'll expand and slow down, and expand and slow down, and expand and slow. And maybe it'll keep expanding forever and keep slowing down and never reverse. Or maybe it'll reach some maximum size and recollapse and reverse, and we'll get a big crunch. Or maybe it'll do like your student loan debt, and it'll just asymptote to zero, but never go away completely, right? Maybe it'll just slow and slow and slow and slow and never quite reach zero balance. So this would explain some things, right? If your universe inflates instead, that means if it starts off a certain size, then it doubles and doubles and doubles in size after a certain amount of time elapses. And then when that time elapses again, it doubles again and doubles again and doubles again. And then it doubles again and again and again each time that time elapses. So if this takes 10 to the minus 35 seconds to double in those dimensions, then by the time 10 to the minus 32 seconds have gone by, something that was the smallest scale where physics makes sense, the Planck scale, 10 to the minus 35 meters in all dimensions, would be blown up in 10 to the minus 32 seconds to being larger than the entire observable universe with a 92 billion light year diameter is today. And this is sort of like imagining, look at A, B, C, and D up there. It's all the same sphere. The only difference is the scale at which you zoom in on it. If I asked you if the earth was round, you'd tell me, yeah, of course the earth is round. I'm not a flat earther and I'm not an idiot. I've seen all the evidence. But if I only said to you, okay, prove to me the earth is round, but all you can do is measure your own backyard, you would be stuck with something like panel D. You don't have enough information because you're too zoomed in. So maybe the reason the universe appears flat today is because whatever topology or curvature it started out with, whether it was spherical-like or torus-like or saddle-like or Pringle chip-like or whatever, maybe the part of it that we can see got stretched so much that it's indistinguishable from flat today. Maybe the reason the universe is the same temperature in all directions is because long ago, everything that is now our observable universe was causally connected in this tiny, tiny volume. And it's just that it was inflated and inflated and inflated, that now what we see as, oh, it looks independent today. No, but they were all part of the same region. And then you say, what about my magnetic monopoles? What about my leftover high energy relics? Well, that's fine if you had a bunch, but inflation happened, then they all got inflated away, and you can have at most one of them within your observable universe. And finally, you can say, okay, but what about those seed fluctuations? What about the original spectrum of underdensities and overdensities? Where did they come from? And you say, okay, well, imagine that you have a universe stretching and stretching and stretching like you do during inflation, but now add quantum fluctuations to that at all scales. So you have a quantum fluctuation and the universe expands, so the fluctuation gets stretched to larger scales. Now you have a new fluctuation and it still gets stretched, so the original fluctuations are on even larger scales, the newer fluctuations are on smaller but still large scales, and now you get new fluctuations on the smallest quantum scales, and this produces a seed spectrum of fluctuations. So you say for the first fraction of a second we had inflation, and then inflation came to an end and we got the hot big bang, and that gave us our seed fluctuations, but it also only got us up to a certain finite temperature, and then we come through our cosmic history and we form, you know, we have the Higgs symmetry break and we give mass to the fundamental particles, and protons and neutrons form as we go from a quark gluon plasma to hadrons, and then the weak interactions freeze out, you get big bang nucleosynthesis and you make the light elements, and then matter starts dominating over radiation because the universe has cooled enough and stretched to longer wavelengths, and you make neutral atoms, and that's where you see the cosmic microwave background, and then you form the first stars, and then you find the earliest galaxies, and then expands, grows, galaxies, stars, and eventually humans. So our cosmic timeline looks like this. You say, all right, for the first 10 to the minus 32 seconds, at least, because we can only observe what's imprinted on our observable universe, which is the final 10 to the minus 32 seconds of inflation. That's what we had. That's how we get the initial conditions that set up the Big Bang. That's how we get the seed fluctuations that lead to the large scale structure in the universe. And it's too long for this talk, but we have other observable tests of inflation where you compare them against the hot Big Bang without inflation, and inflation has won all of them, and the hot Big Bang without inflation is not consistent with observations. Then inflation ends, the universe reheats, we get the hot Big Bang, we get baryogenesis some way, somehow. We don't know how, but we know that we live in a universe where all the stars and galaxies and planets are made of matter and not antimatter. So where did all the antimatter go? Well, at some point, we had to have something generate a matter-antimatter asymmetry where matter wins out, and we don't know what that was. We also know at some point dark matter was generated, but we don't know what that is. We can only see its gravitational effects. The electroweak symmetry breaks. You get the Higgs particle. It gives mass to all of the fundamental particles. Protons and neutrons form because we transition away from the quark gluon plasma. Weak interactions freeze out, which means the neutrino temperature is 4/11ths to the 1/3 power, or about 70% of the photon temperature, because the weak interactions are important. All the neutrinos are in thermal equilibrium, but then they freeze out and they're not in thermal equilibrium. And so when electrons and positrons, the lightest mass charged particle, annihilate, they heat up the photons, but not the neutrinos. That's why the cosmic microwave background is 2.7 Kelvin, but the cosmic neutrino background is only 1.9 Kelvin. Then we have Big Bang nucleosynthesis, where you make the light elements. Then you make neutral atoms, where you have your atomic nuclei and electrons bind together and don't get blasted apart. Gravity gets to work and you start to form clumps of matter. And whereas other stories used to say, oh, you probably don't get the first stars till a few 100 million years have passed. No, it's earlier than that. You probably get stars certainly within the first 100 million years of cosmic history, and maybe even when the universe is just 30 million years old. The earliest galaxy we found is only 285 million years old. So there's a big gap there between the limits of what the James Webb Space Telescope can see and how far back we can see. Then dark energy dominates matter and radiation, Earth forms, and we come to today. I have more I could talk about, but you have questions. So why don't we pause here, and I'll stop sharing my screen. I can hit that little red button. There we go.
Okay.
And
Um,
hopefully we can get to some good questions.
Well, I'll tell you what, we always have a pretty lively chat here. People are they're nerdy and they like puns, and you have scratched everybody's itch today, so thank you for that. Let me see. Because I know there was a question early on here somewhere, maybe not. Where was it? Hold on, I can do this. Um, because I know there was a question. If you did type a question, feel free. Okay, here we go. This is the one that I saw. And I hope I
Great.
get your name right. Saroj, I believe is how you pronounce it, says, "This is fascinating, hearing that the universe is an organism in itself. Question, what is the universe part of that is greater than itself, not a spiritual implication?"
Okay, so if you take as true quantum mechanics and inflation, then you have to say, okay, I can view one way I can view inflation, and this is a way I learned it, and it's the way Alan Guth formulated it, and so it's kind of like the standard picture is you say, I can imagine that you've got a hilltop, like a plateau, and you've got a ball there. And as long as the ball stays up on the top of the hill, you get inflation. But if the hill has edges, and if you roll down into the valley on either side, the rolling down into the valley and oscillating down in the bottom of the valley, that's how inflation ends, and you get the hot big bang. So you say, okay, if I was just a classical field, then that'd just be like a ball. And as long as I stay up here, I get inflation. And when I roll down, inflation ends everywhere at once. And I get a hot big bang everywhere. And that would be one really, really big universe. But we know that quantum physics exists and that at a fundamental level, quantum fields and quantum particles are not just like little balls on top of a hill. They are waves, which means they have a probability distribution that spreads out over time. So if I start rolling one way, if I roll slowly enough, then as my wave function spreads out, parts of that wave function are going to go down the hill really easily, and boom, inflation ends and I get a hot big bang in a universe. But parts of it, if I'm rolling slowly, are actually going to move backwards towards the top of the plateau, especially if it's flat and rolling slowly. This leads to the condition, what we call eternal inflation, where every time our universe, let's say, doubles in size and doubles in size and doubles in size, there might be a couple of regions where inflation ends. But in more regions than there were before the last doubling, inflation will continue. And so those regions are going to double again and double again and double again. And in fact, when you do the math of, well, if I need to get enough inflation so that it's consistent with the observable universe, you can prove this that there will be more regions at all times where inflation continues than there are when inflation ends and you get a hot big bang. So this is our picture of what we call the inflationary multiverse, where our universe where we got the hot big bang is just one place where inflation came to an end, and it is surrounded by more inflating space where within it, yes, you have other regions that end and new hot big bangs, but you can also prove that based on the ways the universe expands when it's full of matter and energy versus the way it expands when it's full of inflation, that these separate bubble universes never touch and never collide. And so that's what's larger than the universe is the inflationary multiverse within the context of eternal inflation. Now, not everyone believes in eternal inflation, but I think, look, quantum mechanics is pretty stable. Inflationary cosmology is pretty stable. And if you put these two together, you can't avoid it. So you can't get observable evidence for it, but also this is kind of the default position. So I would say that's what's bigger than the universe, not from a fairy tale perspective.
Okay. There's a lot of discussion about just you in general and how compelling you are to listen to. I commented I have a new appreciation for facial hair. Ian says that
Ooh,
your eyebrows are
fancy,
very
fancy.
interesting to watch, and he also wants to know he wants to play board games against you and get beaten, basically. So I don't know if that's a weird kink that he has, but it's
You can, look, we all have our proclivities, but I will say I am a big fan of cooperative board games. I enjoy games like Sky Team, the Forbidden series, and games where you work together to beat the game. Arkham Horror is a great example. The games where we try and fight each other, there's enough of that in real life. I like to work together to build things.
I think he's on board with that, and he's calling out a game called Spirit Island. So
Maybe
perhaps you all.
someday, maybe someday we'll get to do it.
Okay. And everybody in this chat is much smarter than I am. I became an English teacher for a reason, not a science teacher, but I'm fascinated by everything and I'm glad everybody here is smarter because they're asking really good questions. Let's see. And there's a lot of them. So there's a whole joke about a bunch of things. We have such a fun chat. Okay. Okay, hold on. Uh, yeah, anyone else have the impression that each sentence Ethan Spiegel says would require a semester-long course to fully explore? Yes, absolutely. Let's see. Um, John is saying he's a fellow medium author. Please read and clap my account of how I challenged a creationist in the Grand Canyon recently. Oh, I'm gonna save that and bookmark it. Let's see. Okay, here's one from Erica, a true scientist. Is matter and antimatter observationally distinguishable? If there were antimatter regions of the universe, could we tell they were antimatter?
So that's a great question. Yes, they are observationally distinguishable. It's subtle. It usually has to do with how a particle's spin is related to to certain of its other properties. So you can distinguish it in a lab. But if you don't want to do that complicated measurement of like, oh, well, what's the CP violating phase of this, particle that you're made out of, like you can just say, look, the biggest thing that makes matter and antimatter different is they are each other's antiparticles, which means when they collide, they annihilate and they emit gamma rays. And that gamma ray signature is observable. So, for example, around the supermassive black holes that are active, we know that these are little factories. They accelerate things to such high energies that they make pairs of electrons and positrons, which are the antimatter counterpart of electrons. And then we see the positrons annihilating with more electrons, and we see a big 500 keV peak photon emission line. That's a signature of matter antimatter annihilation. So the way we tell that matter and antimatter don't both copiously exist in the universe is we have all of these systems where galaxies collide, where clusters of galaxies collide, where different parts of the cosmic web are interacting with each other and merging together. And the fact that we don't see gamma ray annihilation, the fact that we don't see the matter antimatter annihilation signals tells us even on the largest cosmic scale, 99.9999% of the universe is made of matter, and the antimatter part can be no more than 0.00001%. And if you go to smaller scales, like groups of galaxies or individual galaxies or stars, those constraints are even tighter. So the worst constraints still tell you overwhelmingly matter, no evidence really for antimatter except in trace amounts.
Okay, let's see. I saw another question. Uh, if the whole, okay, this one comes from James. If the whole universe is infinite, couldn't there be multiple Big Bangs happening?
Yeah, in fact, we bet there are, right? But the problem is we can only observe our observable universe. We can't even see our whole universe. We just know what's happening in this observable part because light that was emitted at the moment of the Big Bang travels in all directions at the speed of light. And some of that light is just arriving now at our eyes from all directions. That's the limit of what we can see. That's how, in a 13.8 billion year old universe, we can see 46 billion light years away. Because if you said, I'm going to let this light travel for 13.8 billion years, right? The universe has been expanding this whole time. So this thing that was a lot closer to us than 13.8 billion years when that light was emitted, a lot closer than 13.8 billion light years away, it started traveling, but the universe expanded. And the light kept traveling, but the universe expanded. And it keeps traveling, but the universe expands, but the
Yeah.
expansion slows. So eventually, even though it's still expanding, the light reaches us. That initial object that emitted that light, or that initial point in space where that light came from, today is 46 billion light years away. That's what happens in the expanding universe. So you say, yeah, we should. I told you the story about inflation and how it ends and what that means for eternal inflation and what that means for different disconnected universes. They're probably out there, but we can't see them because we can't even see all of our own universe. In
Yeah.
fact, if you waited, right, because you're patient and you lived billions and billions of years, I said today we can see light from objects that's 46 billion light years away, but there's still light behind it that's on the way from things that are too distant to see. And if you wait long enough, you'll actually be able to see the objects that are up to 61 billion light years away today. And if you do your three-dimensional calculation, that's more than double the volume of our presently observable universe.
Wow. Yeah, I mean, there's light at the end of the tunnel, but it may be 61 billion light years away. I love that. You've really scratched an itch for a lot of our sciencey folks here, and I feel like I would have done a lot better in all of my science courses from high school to post-secondary if I had had you. You're just super animated and fun, and even though I only understand a bit of what you're talking about, it makes me want to learn more. So I want to say thank you for that.
Well, you can only do so much in 1 hour, but hopefully this gave you a little teaser for what are some of the things that we learn about, that we study, that we try and make sense of, and that you're up to the cosmic frontier on some of this. Like, this is what we know today. This is the limit of what we know today. And hopefully, we will launch the Nancy Grace Roman Space Telescope. We will continue learning things from the James Webb Space Telescope. We will get the Dream Observatory of the Habitable Worlds Observatory. Maybe we'll build the next generation very large array like the Astro 2020 Decadal recommended. Maybe we'll build LIGO 2, or at the very least, maybe we'll keep both LIGOs running for a while. Maybe we'll get the LISA mission in space to get gravitational waves from supermassive black holes, not just solar mass ones. There's so much more to learn, right? We learn by pushing the cosmic frontier, by seeing what's over the next horizon. And although I fear for a day where we stop doing that, where we stop investing in that, I still think that long term, the future is going to be bright. You might say right now in the 21st century, things are pretty bad. And I can't disagree, but I can say we're still going to be the human enterprise in the 22nd century and in the 30th century. And we have not learned all there is to learn or anything close to it. So let's keep going and follow science, knowledge, reason, and use that to inform the decisions we make on Earth, having the best information available.
I always end our discussions by asking folks what gives them hope, but I kind of feel like you maybe just answered that.
Oh, well, I don't believe I have psychic powers, but every once in a while, you're just on the same wavelength. Maybe it's because when I run my own podcasts, I always end by asking my guests if they have any final thoughts for my listeners out there. And I thought I'd give you some of mine.
Well, I mean, I'm not even going to ask the question because I think you just gave us a whole bunch of hope and a whole bunch to think about and a whole bunch to read. Lindsay did put the link to his podcast up on the chat, so you can access that.
Yeah,
Starts
everything I
with
do
the
is under Starts with a Bang. I'm Starts with a Bang the blog, Starts with a Bang the website, Starts with a Bang. Maybe someday we'll have Starts with a Bang the frozen yogurt, but right now we have Starts with a Bang the podcast also.
Well, we've already decided that we're going to create a series of food and drink products called the medieval fireballs. So yeah, there's a lot
Mm.
happening here, and we look for.
Primeval fireball is the way to
Oh,
go.
sorry. Yeah, primeval. Did I say medieval? I meant
It's
primeval.
okay.
Sorry. See again, English
English major,
English
what can you
teacher.
do,
Yeah.
right? That's right.
All right. Well, I appreciate you so much, Dr. Siegel. Thank you so much for brightening our Friday. And come back anytime you want to.
Well, thank you so much, and keep looking to the universe itself for all your cosmic answers. It won't disappoint you.
That is great advice. Thank you so much, everybody. Have a great weekend, and we'll see you next weekend. Thank you.
Right.